The set of operations including select sigma, project, union, difference, rename, and Cartesian product X is called a complete set because any other relational algebra expression can be expressed by a combination of these 5 operations. For example, R intersect S equal to R union S minus R minus S union S minus R. R theta join condition S equal to sigma join condition. Division operation. The division operation is applied to 2 relations. R, Z, dividing by S, X, where X subset Z. Let Y equals Z minus X, and hence Z equals X union Y, that is, let Y be the set of attributes of R that are not attributes of S. The result of division is a relation T, Y, that includes a tuple T if tuples TR appear in R with TR, Y, equals T, and with TR, X, equals TS for every tuple TS in S. For a tuple T to appear in the result T of the division, the values in T must appear in R in combination with every tuple in S. The slide is the example of the division operation. A. Dividing SSN underscore nose by Smith underscore nose. B. Dividing R by S. Table 8.1 is the summarization of all operations of relational algebra that we have learned. Select, project, theta join, equijoin, and natural join. Table 8.1 is the summarization of all operations of relational algebra that we have learned. Union, intersection, difference, Cartesian product, and division. Query tree. An internal data structure to represent a query. Standard technique for estimating the work involved in executing the query, the generation of intermediate results, and the optimization of execution. Nodes stand for operations like selection, projection, join, renaming, division. Leaf nodes represent base relations. A tree gives a good visual feel of the complexity of the query and the operations involved. Algebraic query optimization consists of rewriting the query or modifying the query tree into an equivalent tree. This is the example of query tree corresponding to the relational algebra expression for Q2. A type of request that cannot be expressed in the basic relational algebra is to specify mathematical aggregate functions on collections of values from the database. Examples of such functions include retrieving the average or total salary of all employees or the total number of employee tuples. These functions are used in simple statistical queries that summarize information from the database tuples. Common functions applied to collections of numeric values include sum, average, maximum, and minimum. The count function is used for counting tuples or values. Use of the aggregate functional operation F. Fmax salary, employee, retrieves the maximum salary value from the employee relation. Fmin salary, employee, retrieves the minimum salary value from the employee relation. Fsum salary, employee, retrieves the sum of the salary from the employee relation. Fcount SSN, average salary, employee, computes the count, number, of employees and their average salary. Note, count just counts the number of rows, without removing duplicates. The previous examples all summarized one or more attributes for a set of tuples. Maximum salary or count, number of, SSN. Grouping can be combined with aggregate functions. Example, for each department, retrieve the DNO, count SSN, and average salary. A variation of aggregate operation F allows this. Grouping attribute placed to left of symbol. Aggregate functions to right of symbol. DNOF count SSN, average salary, employee. Above operation groups employees by DNO, department number, and computes the count of employees and average salary per department. Figure 8.10 is the example of the aggregate function operations. A is to find number of employees and the average salary group by department. The operation, B, produced the same result in A. C is to find the total number and the average salary of all employees. Recursive closure operations. Another type of operation that, in general, cannot be specified in the basic original relational algebra is recursive closure. This operation is applied to a recursive relationship. An example of a recursive operation is to retrieve all supervisees of an employee at all levels, that is, all employee directly supervised by E, all employees E directly supervised by each employee, all employees E directly supervised by each employee, and so on. Although it is possible to retrieve employees at each level and then take their union, we cannot, in general, specify a query such as retrieve the supervisors of James Borg at all levels without utilizing a looping mechanism. The SQL3 standard includes syntax for recursive closure. The outer join operation. In natural join and equijoin, tuples without a matching, or related, tuple are eliminated from the join result. Tuples with null in the join attributes are also eliminated. This amounts to loss of information. A set of operations, called outer joins, can be used when we want to keep all the tuples in R, or all those in S, or all those in both relations in the result of the join, regardless of whether or not they have matching tuples in the other relation. The left outer join operation keeps every tuple in the first or left relation R in R left outer join S. If no matching tuple is found in S, then the attributes of S in the join result are filled or padded with null values. A similar operation, right outer join, keeps every tuple in the second or right relation S in the result of R right outer join S. A third operation, full outer join, denoted by the symbol as shown in the slide that keeps all tuples in both the left and the right relations when no matching tuples are found, padding them with null values as needed. Figure 8.12 is the result of a left outer join operation.